Okay, welcome back to the session. The last talk in this meeting is from Professor Deanna Lacoste from KAUST. Deanna has been working in plasma for a long time, particularly flame-assisted plasma. She did record the talk, but I understand she will be there to answer questions after. So I will just play the video, and after that we will have some discussion.
Good afternoon. I am Deanna Lacoste from KAUST, and in this video, I will give an overview of what has been done so far in the research field of plasma-assisted ammonia flames. My co-authors for this presentation are Nader Shodi and Medine Ali Sharif. This presentation will have 4 parts. First, I will introduce plasma-assisted combustion. Then I will make a short review of the papers that are reporting studies on plasma-assisted combustion of ammonia. I will present our recent results in plasma-assisted ammonia flames. And I will conclude with the key challenges in this field. Let's start with the introduction of plasma-assisted combustion. Plasma-assisted combustion, also called PAC, is a process of enhancing combustion with electric discharges. Then you may ask me, what is an electric discharge? An electric discharge is the process of turning a gas into a conductive media by applying an electric field. In this photograph, you can recognize a lightning. A lightning is an example of electric discharge. But closer to combustion problems, here you can recognize a spark plug, and the white light here is the light emitted by a spark. This system has been used in internal combustion engine for more than a century. Typically, they have an energy deposition in the plasma between 20 and 200 millijoule. The plasma duration is around 1 millisecond, and you can have a strong gas heating by the plasma with a temperature of the gas that can reach 10,000 Kelvin. 10,000 Kelvin, it's really a lot of heating. And for combustion application, you don't need to reach such a high temperature to have an effect on the flame. Anyway, it's difficult to control this temperature. And with the technology that they have in the 20th century, they could not have a better control. But nowadays, we have a better system that can be more efficient in improving or enhancing the combustion. But before we go into this kind of system, how does it work? How can we enhance combustion with plasma discharge? Here in this photograph, you can see multiple plasma filaments, multiple electric discharges, produced between a rod and an annular ring. And this discharge, they can enhance the combustion by different ways. First, they can enhance combustion by a radiative effect, because you can see they are emitting visible light, but they are also emitting UV light. You can have a chemical effect with production of atoms, such as atomic oxygen, atomic hydrogen, or atomic nitrogen, but also production of excited species, such as excited nitrogen, or molecules and radicals, such as NO, NH, or ozone. You can have a thermal effect with the fast gas heating and the slow gas heating. Here, I'm making the differentiation because slow gas heating is when you have a heating that's happening in the time scale of 100 of microsecond or millisecond. This is considered as slow. Fast gas heating is a heating that's happening at the nanosecond time scale. When you have heating happening at the nanosecond time scale, you can consider that you have a constant volume heat addition. Therefore, after the heat addition, you will have gas expansion and generation of shock waves. And this can lead to the fourth effect of plasma on combustion by changing the transport properties by this shock waves and this gas expansion. But also, even if you don't have any strong thermal effect, if you change the chemistry, you will change the diffusion properties of your media. In plasma-assisted combustion, it is considered so far that the radiative effect is negligible. Therefore, the effect of the plasma on combustion can be by chemical effect, thermal effect, and/or transport effect. So there are different ways to play with these parameters, and a really versatile plasma system, and the one that is the most commonly used in the plasma-assisted combustion community, are the nanosecond repetitively pulsed discharges, also called NRP discharges. These discharges, they are produced by applying ultra-short pulses in the range 1 to 100 nanoseconds of high voltages between 5 and 100 kilovolts at a high repetition rate with a pulse repetition frequency, or PRF, in the range 10 to 100 kilohertz. And the interesting point is that by playing with any of these parameters, pulse duration, applied voltage, and pulse repetition frequency, you can completely change the properties of your plasma. Here, in this example, I'm showing 3 different regimes of plasma obtained between 2 pins in air. In this example, we keep constant the pulse duration, we keep also constant the pulse repetition frequency, but we increase the applied voltage. And we can see that we have a transition between a corona plasma, a glow plasma, and a spark. In this presentation, I will focus on the NRP spark discharges, because these are the discharges that has been the most commonly used. In this photograph, I'm showing an example of these NRP spark discharges located at the outlet of the injection tube of a swirl stabilized flame. It was for a swirl stabilized methane air flame. And typically, for this kind of discharges, you will have an energy per pulse which is in between 1 and 20 millijoules. You will have a strong chemical actuation with fuel cracking and dissociation of molecular oxygen. You will have a strong fast gas heating with up to 4,000 Kelvin temperature rise in about 50 nanoseconds. And then you will have strong transport effect with generation of shock waves and gas expansion. So this type of discharges has been really efficient in enhancing the combustion of hydrocarbons. They have been used to enhance the ignition of different types of hydrocarbons in constant volume combustion chambers, but also in AC engines and in scramjets. They have been used to enhance the burning velocity of laminar flames, turbulent flames, but also on detonations. They have shown that they could enhance the lean blow-off limit and the stability limit of swirl stabilized flames and bluff body stabilized flames. And they were also used to control thermoacoustic instabilities. Let's now move to what has been done in plasma-assisted combustion of ammonia flames. The total number of papers reporting plasma-assisted combustion studies is larger than 1,000, but among them, less than 1% focus on the combustion of ammonia, and these papers are very recent. The first paper published in 2018 was a numerical study, and we see the first experimental study of plasma-assisted combustion of ammonia in 2021. In 2022, we had more than 8 papers, and in 2023, these numbers are even increasing. So let's talk about the first paper, the numerical investigation on the effect of non-equilibrium plasma on the laminar burning velocity of ammonia flame, published in 2018 by Shioke and co-authors from a group in Japan. So they used a really simple configuration where they had a plasma that they modeled in a zero-dimensional simulation. And then they had a one-dimensional simulation of a flame stabilized over the burner. They developed a kinetic mechanism for plasma-assisted combustion of ammonia with 20 species and 43 reactions. And they showed that they could increase the laminar burning velocity by up to 15% by applying an electric field with different duration up to 100 nanoseconds. And they obtained this result for equivalence ratio varying from 0.8 to 1.3. So this study is interesting, but they did not compare with experimental results. In 2021, I'm sorry for my presentation. Choi in the group of Wentingson, in collaboration with Tim Ombrello and Campbell Carter, published a really important paper in this field, which is a paper on plasma-assisted ammonia combustion, simultaneous NOx reduction and flame enhancement. This is a key paper in this field because they show that they could decrease the NOx emission of ammonia flames. So in this photograph, I'm comparing their ammonia flame without plasma and with plasma, with NRP discharges for two equivalence ratio, one at 0.94 and one at 0.71. The first result that I wanted to share with you is this one. They compare the equivalence ratio at blow-off for a range of airflow rate, in black for the flame without plasma, and in color for a flame enhanced with plasma. Here there is an interesting result, which is that for a same power of 39 watts, they could either have no effect on the stability limit, have a weak effect, or have a strong effect. The main difference between these three plasma actuation was the applied voltage and therefore the reduced electric field. So in this study, they show that to enhance the lean blow-off limit of ammonia flames, it's not the power that is really important, it's much more the reduced electric field and therefore the chemistry that will be produced by the discharges. The second important result is this one, where they compare the NOx emission in the burn gases of the flame without plasma, a little bit more than 2,500 ppm, and for the same condition when they apply three different plasma by increasing the power between 20 watt in green to 59 watt in red. And they observe that they have a really strong NOx reduction by about 40%. So the community was really happy with this result because plasma could be used to reduce the NOx emission in ammonia flames. But then I raised the question, okay, how does it work? How can you explain that you are changing the NOx emission in ammonia flame with a plasma, specifically with a plasma that is NRP spark discharges that is known to produce NOx because you have a strong gas heating. Indeed, it has been demonstrated that when you apply NRP spark discharges in air-containing mixture, you can produce a concentration of NOx in the range 10 to 100 ppm. But here we are talking about thousands of ppm. So we might have a different effect of the plasma on the chemistry of the combustion, but also on the thermal NOx production. In this study published in 2022 from Kim et al. From a group in Korea, they showed the effect of non-thermal plasma on turbulent premix flame of ammonia air in a swirl combustion. So they use the different types of plasma, but really similar to NRP spark discharges. Again, comparison between no plasma case and plasma assisted ammonia flames. They show that the flame was more stabilized. Again, they obtain a NOx reduction. Here, the concentration is lower because it has been corrected on the basis of 15% of oxygen content in the exhaust gases. And they show that for lean flames and stoichiometric flames, they could decrease significantly the NOx concentration in the exhaust gases. They started to investigate how this could happen by measuring the intensity of the NH2 star chemiluminescence. In black here for the flame without plasma, and in color with the plasma. And here what you can see is that you have an increase in the intensity of the chemiluminescence of NH2 star. They concluded that NOx can be reduced with non-equilibrium plasma with high discharge power and by decreasing the flow residence time in the combustion. Again, in 2022, a follow-up of their study in 2021, Koe and Sun published a study on the experimental investigation of non-equilibrium plasma-assisted ammonia flames using NH2 star chemiluminescence and OH, planar laser-induced fluorescence. So in the paper, you can find some examples of NH2 star chemiluminescence images and OH images for different conditions. Interestingly, they compared for a combined measurement of OH and Abel inverted NH2 star chemiluminescence. And they concluded that OH and atomic oxygen may play an important role in the generation of NH2 star in the presence of plasma discharges. Another interesting paper published by Tang et al., a group in China, on the flammability enhancement of swirling ammonia air flame combustion using AC-powered gliding arc discharges. This is, again, a bit different than NRP spark discharges, but the property of the plasma are really similar. They made measurement of NO concentration and NO2 concentration in the exhaust gases, in black without plasma and in red with plasma. Two interesting results. They show that when they could stabilize the flame without plasma, there is no much effect on the plasma on the NO and NO2 concentration. But as they could extend the stability of the flame at lower equivalence ratio, they could reach conditions for which the NOx content were relatively low. They also performed NH2 star chemiluminescence imaging and OH measurement. And they concluded about the competing mechanisms. They said that the plasma could increase the NH2 star and therefore triggering the thermal denox process. But the plasma was also a source of increase of thermal NO. In this study, focusing more on the chemistry, Chen et al., in the collaboration between a university in China and in Sweden, proposed an experimental and kinetic modeling study of the laminar burning velocity enhancement by ozone additive on ammonia air flames and blend of ammonia and hydrocarbon air flames. Here, they didn't directly apply the plasma. They used ozone additive as a tracer of the chemical effect of the plasma. They used a McKenna burner with a flat stabilized flame, and they compare the chemistry and the combustion, the laminar burning velocity, of the flame of ammonia air mixture and ammonia air mixture with an addition of 5,000 ppm of ozone. They show that they could enhance the laminar burning velocity around 5%. Look at the large error bar, so it's difficult to make a clear conclusion. And anyway, they compare the experimental result with different kinetic models, and they were in good agreement. They also perform more in-depth analysis of the chemical pathways. And finally, I wanted to show this paper that has been published also in 2022 from a group in China, Zhu and co-author, about the investigation of the spectral characteristic of gliding arc plasma-assisted ammonia lean combustion. Again, gliding arc plasma, but here they focused on the spectral emission. They performed comparison between different conditions for the H alpha chemiluminescence, NH, atomic oxygen, atomic nitrogen, and N2CB, mainly for equivalence ratio, really lean equivalence ratio, less than 0.5. They also performed temperature measurement by comparing the spectra of N2CB, the 00 band, with numerical simulation, and they claimed that they could estimate the temperature. Here, if you look at this comparison, this is not precise enough to be really confident with the temperature that they were showing. In addition, here you have the peak of NH star that they didn't take into account in their simulation. So yeah, this is a first attempt, but further work is needed to have a clear understanding of the thermal effect and the chemical effect of the plasma. Let's now present our recent result on plasma-assisted ammonia flames. First, I would like to say that these are preliminary results. The main part of the result that I'm going to present today are unpublished results, and we are confident that they are correct, but we don't have the complete explanation of what we have observed. We have used this experimental setup where we have a swirl stabilized flame over a bluff body, with the bluff body connected to the high voltage of NRP discharge generator and the outlet of the injection tube connected to the ground. We tested different fuels from pure ammonia to ammonia crack between 10 and 28%. This cracking was not a real cracking. We were actually using mixture of ammonia, hydrogen, and nitrogen to mimic the cracking of ammonia. And we use NRP spark discharges with a constant pulse repetition frequency of 30 kilohertz, an applied voltage varying from 3.5 to 5.5 kilovolt, and the corresponding power of the plasma between 3 and 100 watts. At the bottom part of the burner, there is a loudspeaker that allows us to make acoustic forcing of the system. Here in these two photographs, you can see a flame, ammonia flame without plasma, and then the same flame with NRP spark discharges. You can see that the flame is a bit more compact, showing that you have a faster burning rate for the flame. And we have performed some measurement. We have performed NOx measurement in the exhaust gases. We have measured the velocity inside the burner with a hot wire, and we have collected the OH star chemiluminescence of the flame with a PMT. We use this OH star chemiluminescence as a tracer of the heat release rate. So these are the first results that we have obtained for the enhancement of the lean blow-off limit. So this is, in this graph, I'm showing the equivalence ratio at blow-off as a function of the bulk velocity. In black are the result obtained without plasma, and with the open symbol, these are the results obtained for a flame enhanced with plasma produced by 5.5 kilovolts of applied voltage. This corresponded to a plasma power of about 100 watts. So for pure ammonia, we can see that we are enhancing significantly the equivalence ratio at blow-off, mainly for low velocity. Now, if we use ammonia with a 10% cracking, we can see that there is also a plasma effect on the limit at blow-off, but it's a bit less. An interesting comparison is for low velocity. The plasma effect is similar to 10% of cracking of the ammonia. If now we see the plasma effect on higher level of cracking, 20% of cracking, the plasma effect becomes marginal. And if we move to 28% cracking, the plasma effect is detrimental. So this is really important because it's not when you have a flame, any flame, when you are applying a plasma, any plasma, you will not necessarily have a beneficial effect. So you need to understand what's happening and how to apply which kind of plasma in order to achieve what you are expecting. In the following part, I will focus on measurement that has been performed, for a bulk velocity of 7 meters per second. Now I'm going to present the result that we have obtained for the NOx concentration at the exhaust. So here I'm showing the corrected concentration of NOx for 15% of oxygen in the exhaust gases. So for pure ammonia, we have this amount of concentration of NOx as a function of the equivalence ratio. And we obtain this result for 10% cracking, 15% cracking, and 20% cracking. Here we are reproducing some results that have already been published by others, meaning that for a given equivalence ratio, when you increase the percentage of cracking, you are increasing the concentration of NOx in the burn gases. But as you can stabilize flame at lower equivalence ratio, you can eventually reach conditions for which you have a low concentration of NOx in the burn gases. In this study, we tried to focus on concentration of NOx lower than 200 ppm, because this is the upper limit to reach 10 ppm after conventional denox processes. So here, with 10% cracking, 15% cracking, and 20% cracking, we can reach condition where we have this less than 200 ppm of NOx in the burn gases. What about with plasma actuation? So again, I'm plotting the same concentration of NOx produced by pure ammonia flames. If we apply a plasma with an applied voltage of 3.5 kilovolt, there is no much effect. For 4.5 kilovolt, we start to see an effect, but we are in the error bars. At 5 kilovolt, we can start to see a significant effect at equivalence ratio close to 1. But more interestingly, we can start to stabilize the flame at lower equivalence ratio and therefore reaching low concentration of NOx. And this is even more obvious with a plasma obtained with a 5.5 kilovolt applied voltage. So also with plasma, without any cracking, we can reach a concentration of NOx in the burn gases less than 200 ppm. This result is interesting, but note that for this condition, the plasma power was about 2% of the flame thermal power. This is quite a lot. In my previous study, I tried to never exceed 1% of the flame thermal power, but here we had to reach 2%. This in the future will have to be compared with the thermal energy that is required for cracking of ammonia. Let's now look at how the flame responds to acoustic perturbation of the fluid. So these studies are important to help in understanding the response of ammonia flame to thermoacoustic instability, to see if this kind of flames could be susceptible to thermoacoustic problems. So for that, we will be using the flame transfer functions formalisms, meaning that we will be comparing for the forcing at in the range of frequencies between low frequency and high frequency. We will be comparing the relative fluctuation of heat release rate with the relative fluctuation of velocity. And we will plot the data as a function of a gain and a phase. If the gain is higher than 1, this means that the flame is amplifying the perturbation. If the gain is lower than 1, this means that the flame is damping the pressure. The phase corresponds to the time delay between the arrival of the perturbation at the base of the flame and the time for obtaining the response of the flame. So recently we published this paper comparing the flame transfer functions of pure ammonia flames and ammonia partly cracked flames. In black, you can see that for pure ammonia flames, the gain is almost always below 1, meaning that the flame is always damping the acoustic perturbation. This means that these ammonia flames will not be susceptible to thermoacoustic instabilities. But when you start to crack the ammonia, in blue for 10% cracking, in green for 20% cracking, and in red for 28% cracking, you will have some condition, some frequency for which you have a gain that is much higher than 1, meaning that the flame is amplifying the acoustic perturbation. And in this case, these flames can be susceptible to thermoacoustic instabilities. So we wanted to see if plasma could help in resolving this problem. But as pure ammonia flames were not really concerned by the problem, we focused on enhancing the response of the flame to acoustic modulation for ammonia at 10% cracking. So this is what I'm showing here. Note that we have changed the equivalence ratio to take an equivalence ratio of 0.8 in order to be in condition for which the NOx emissions were relatively low. These are the gain and the phase of the NH3 at 10% cracking ammonia flames without any plasma. When we apply a plasma for an applied voltage of 3.5 kilovolt, there is no much effect. At 4.5 kilovolt, we start to see an effect, but we have a reduction of the gain at low frequency, but an increase of the gain at high frequency. Again, this shows that the plasma effect is not necessarily always a positive effect. When we increase the applied voltage at 5 kilovolt and 5.5 kilovolt, we could obtain a flame that almost never responds to acoustic modulation of the flame. So this is a good result, and it was obtained, for a plasma power that was about 2.5% of the flame thermal power. So again, this is much higher than the plasma power that we have used for the control or for the enhancement of hydrocarbon flames. So in conclusion of our recent result, we have reproduced previous results from the literature. And we have found a plasma condition that can simultaneously enhance the blow-off limit, reduce the NOx concentration at the exhaust, and mitigate the response of the flame to acoustic perturbation. Let's now move to the key challenges. The first one is the optimization of the plasma effect to have a plasma-assisted ammonia combustion similar to methane combustion at low energy cost. This means that we want to have a plasma-assisted ammonia flame that is more efficient than burning ammonia that has been partly cracked, either by thermal or catalytic cracking. And we are far from this result. This requires much more work. The second important point is the development of plasma-assisted ammonia oxidation kinetic model. This is really important. We will not succeed in the first point if we don't have a good understanding of the chemistry in plasma-assisted ammonia flame. And for that, we need experimental data of the chemical species involved. I'm not talking about chemiluminescence, I'm not talking about excited species that we can easily measure by chemiluminescence. I'm talking about quantitative measurement of key species in the chemistry of ammonia. And finally, I think it's important to demonstrate the plasma effect during the combustion of liquid ammonia. In real application, ammonia will be injected in a liquid form, and we need to show or to demonstrate that the plasma can have an effect in this condition. This will be complicated because it will be a three-phase reactive flow with a liquid phase, a gas phase, and a plasma phase. With that, I thank you, and I'll be happy to answer any of your questions.
Hi, Deanna, can you hear me?
Yes, can you hear me?
Yes, you can. Well, thank you for this really interesting talk, very informative, and I like it that you also provided future direction as well as what has been done thus far. So the paper is open to the question. Please, for questions, please wait for the microphone.
Hi, Professor Deanna. How are you? Christian from KAUST.
Hi, Christian.
Yeah, thank you for the presentation, as usual. Very good one. On slide 21, you know that Thibault and I have been working a lot on lean flames, ammonia lean flames, and we observed that the NOx reduction is actually because the N2 is increasing by the far lean equivalence ratio. So have you measured the N2 as well for those far lean flames?
Thanks, Christian. This is a really interesting point. So Nader is currently now in the lab doing this measurement. So yeah, I don't have the answer yet, but this is something that we are monitoring. It's obviously a key species in this game, and we will see. So far as I know, there is no measurement that has been published on plasma-assisted flames, ammonia or other flames, with measurement of N2O. We will see how it goes.
Okay, thank you, Professor.
Other questions? Dan, I may ask, when you're applying the plasma, is the method by which you apply it would determine the efficiency and hence the total power required? Do you apply it directly to the fuel? I mean, this is premix flames. So how is the design of the sort of introduction of the plasma impact on the basically power required?
So thanks, Bassam. This is really an important point. In this recording, I just sometimes mention that, okay, you can have a diverse effect of the plasma. Sometimes it's positive, sometimes it's negative. I'm talking about the plasma power compared to the flame thermal power. This is a key point of in our field. It depends. So it's quite challenging. And so far, there is no real guidance about which kind of plasma plasma promoting thermal effect, chemical effect, transport effect, or a combination of these effects. And there is also no real guidance about where do you put the plasma in your system. It really depends on the effect that you want to obtain. And it's, as far as I know, currently it's on a trial and error based methodology that we are working on that. So it's the experimental investigation of plasma-assisted combustion is quite empirical. We have a community working on numerical simulation and on modeling that is growing, so that's fantastic. But they started maybe 10 to 15 years after the experimental work started, so they are a bit late, so they are catching up, but that's okay. But we are not yet at the point where we can have a direct comparisons between simulation and experiment, and only this combined methodology could help us in developing a new system that will be efficient.
Okay. Yes.
Thanks, Deanna, for the talk. A question. So at some point when you add too much power, well, a larger amount of power, that you're going to start to get thermal heating. And all the results that you've shown so far haven't indicated what you might term a saturation effect, as in that it would look as though the trends that were being reported, if you would have put even more power in, there might have been a further increase, obviously, to some point where you would start to get a thermal plasma. Can you make any comment, literature, your own experience, measurements that you haven't reported here about the existence of such plateau or of the effect?
Yeah, this is a really good point. Thanks for this comment and question. You're absolutely right. When we put a plasma that is heating too much the gas, then we increase the NOx, and we reach conditions for which it starts to become detrimental. So it's not only that we don't have a positive effect on the NOx concentration, but we start to really increase it significantly. We are also, I didn't show the result because they were not validated yet, so I didn't want to give a false impression. We are still working on that. There are other groups who reported that they also observed an increase in the NOx with the plasma. So this initial paper showing that for this specific condition, you had a really beneficial effect on the NOx concentration. It has been reproduced, but if you move just a little bit outside of this condition, in terms of the plasma power, but also in terms of the fuel, this positive effect of the plasma, as far as I know, is mainly on pure ammonia flame. When you start to deal with ammonia flame, ammonia that has been partly cracked, then as far as I know, the plasma is always has always a negative effect on the NOx. So this is just an opening or really interesting question about the chemistry and about competing mechanisms. But again, it's too preliminary to have the answer to this question.
Do you want me to read it?
So there is a question in the Q&A.
It says, thank you for your interesting presentation. I wonder what would be the attainable NOx emission reduction by using plasma technologies, and what can be considered an acceptable trade-off between plant complication and cost and the attainable reduction.
Okay, thanks for this question. So currently we are working on the objective of reaching less than 200 ppm of NOx in the exhaust gases, because this will allow us to use a conventional DeNOx process. We don't have the answer for N2O, so this might be an additional constraint, but I don't have the answer yet. Of course, we'll have to take care of that. In terms of realistic use of plasma actuators in industrial systems, it will depend on how difficult the problem will be to solve. Plasma are expensive technologies, especially the plasma that we are using in research. But the plasma that we are using in research can be translated to much more cheaper plasma, cheaper in terms of capital cost, in terms of maintenance, in terms of operation. So we don't worry about that. What we really worry is the energy in the plasma, because this is something that we'll have to address. And this is why we try to have a plasma power that is as low as possible. Again, in this preliminary work, we are talking about 2%. It's much too high. We are targeting something well below 1% of plasma power compared to the flame thermal power. If we can reach that, this will be a solution that will be comparable to other solutions that are implemented in industrial system for combustion. So we think that we could be competitive.
Thinking about that, Deanna, the energy required to crack ammonia, even electrically, is much higher than 2%, wouldn't it? I think it's more like between 15 and 20%. So you weigh less than what's required. Also, the energy required to do cleaning, if you want to be sort of denoxing or NOx collection, it also is not small amounts, and is so in the scheme of things, it seems to be a cheaper option.
Yes, but Bassam, we are not cracking 100% of the ammonia. So, for example, when we are cracking 10%, my understanding is that for thermal cracking, you need about 30% of the thermal power of the flame, but it's 30% of 10%. So we are around 3%. So with plasma, we are better, but we are comparable. So this is why I'm saying it's really an open question, and we really need to make an effort on that.
But that's also really cost and requires infrastructure as well.
Absolutely. No, it's too. It's not mature enough to have a clear understanding of the potential industrial application. We are really in the proof of concept stage and the physical understanding stage. We are not close to the technology transfer at this point, but I hope obviously that it will be competitive, but I don't have the clear answer at this stage.
I know this may be an extension, but you think it will work under pressure as well?
Yes. Yeah. So the result that I have presented, that I've briefly discussed in my introduction for hydrocarbon flames, they have been obtained at pressure up to 10 bars, demonstrated at pressure up to 10 bars, and without any significant issues with the increase in pressure. I don't see how the fact that we move to ammonia fuel will change anything in this result. So I'm confident that pressure will not be an issue. What will be more an issue will be actually the fuel injection. If we have liquid ammonia, of course, we can always find a solution where we put the plasma in area where the ammonia is already pre-vaporized, or I don't know. But this will also require a lot of effort to understand what will be the best plasma strategy. And here, I'm not sure we can reach something competitive either.
Thank you, Deanna. Any other questions? Okay, if not, then thank you very much. Please join me in thanking Deanna again for her excellent presentation.